Hello again. This is Roger Koch Barr for the Bioelectricity course. We're in week 4. This is segment 7, and this is a problem session. It's an interesting problem session. I think you will enjoy it. Here's our problem. We have active tissue. We want to use the Hodgkin-Huxley standard parameter values that were given a few slides back. We want to use the state variable set number 1 that was given a few slides back. There's no stimulus current at this time. And we're asking for this tissue, this membrane. What are the values of IK, INA, IL, the leakage current? And then the most interesting part, part D, if these currents were maintained without change for 50 microseconds, by these currents, it means IK, INA, and IL. If these currents were maintained without change for 50 microseconds, what would be the change in VM? So let's talk about how that can be computed. First, let's talk about the situation with IK. Now, IK is easy to find because we have an expression for IK. We know that IK equals G bar K into the fourth VM minus EK. That is to say, we know that IK goes as the maximum sodium current that could ever exist if all the channels were open, the probability to the fourth power of one of the particles in a channel being open, and then the potential difference between the VM, which is the present transmembrane potential, and EK, what VM would be if everything was in equilibrium. We have a number value for each one of these from our list above. So therefore, we can just plug in numbers here, 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 do the computation, and we get everything. A similar situation exists for the other two currents. The question asks us to find the INA equals G bar NA M cubed H VM minus ENA. Every one of these numbers is given, so we just read the numbers out of the standard parameter values and the values of the state variables. We read the numbers, we plug them in, we get the result. And similarly, we do the very same thing for IL. IL has an even simpler expression. Put that expression in, do the computation, and then you have it. I'll leave it up to you to actually compute the numbers. Now here we come to the interesting part of this calculation. It says if these ionic currents were maintained without change for 50 microseconds, what would be the change in VM? Now, 50 microseconds is a pretty big time shift to assume that everything remains constant. That is to say, to assume that all the membrane currents, the ionic currents, are remaining constant. If it was a computer calculation, which nowadays is what people usually have, you would not use a step that was 50 microseconds. You would use a much smaller step, maybe 5 microseconds, maybe 1 microsecond. Here, in this case, we're saying 50 microseconds, which is about the outer limit, near the outer limit for hand calculations. Sometimes people use 100 microseconds in hand calculations, and this larger number is used because it's more interesting when you're doing it by hand to see the result. It's a bigger result, and so you get more out of it. It's not hidden in the digits of lower precision. In any event, what would the change in VM be? Now at this point, we don't actually have an expression that's the right expression to use. We'll have to make one for ourselves. What we do have is the expression that was used for passive tissue, and I've written it right here as equation number 1. The problem with equation number 1 is that we have this term Vm over Rm, and we can't make use of that computation because we have no value for Rm. We know that the membrane resistance has changed, most likely, since the membrane was at rest, and we don't have any other value. However, we remember that Vm over Rm is simply the ionic current, and we can get that another way. So we can say Vm over Rm is equal to I ion, and that's equal to Ik plus Ina plus Il. We have just gotten finished computing Ik plus Ina plus Il. Well, at least we computed them individually. So we have values from the earlier parts for this, this, and this. Therefore, what we can do, we can find the sum. So now we will have I ion. And when we I ion, we can use it in place of Vm over Rm and proceed with our computation. So just rewriting the dVm part of the equation, we can say dVm is equal to I stem minus I ion times dt divided by Cm. If we look at this part by part, thinking now in terms of numbers, we have I stem, which is given as 0. We have I ion, which we just computed. We have dt, which is 50 microseconds. And we have Cm, which is 1 microfarad per centimeter squared. So we have all the number values that we need. It's now simply a matter of doing the computation. It's worth noting as we do the computation that at one level we're just putting numbers in an equation and doing a calculation. At another level, when you think about it, we're doing something that is really special. We're taking a set of values that exist at one moment. I stem, I ion, Cm, these all exist at one moment, and now we're extrapolating them so we have an estimate of Vm. We're finding the change between the present moment and Vm at the next moment, or in other words, we're finding the change in Vm as it shifts with time. And that is a new thing and worth reflecting on. Here are the standard parameters that we were mentioning in the previous slide. We could take these values, plug them into the equations on the previous slide, and then find numerical results. Well, with this beautiful shot of the woods along Science Drive at Duke University, thank you for watching this segment. I look forward to talking to you again in the next one.